So welcome back to the final talk of this afternoon session. And this is Professor Diamond's third talk in his series of 4 talks on Serre's conjecture for GL2 orbital Gaussian fields.
Thank you. Like last time, let me give a quick recap and bring this up to where we were, and then I'll see if there are questions before I get going again. So we were looking at the case of GL2 over a totally real field. So the setting of Hilbert modular forms. So we have the Hilbert modular variety, d-dimensional disjoint union of quotients of d copies of the upper half plane, and a moduli space for Hilbert-Blumenthal abelian varieties. And we can consider the space of Hilbert modular forms. So these are automorphic forms with respect to the group restriction of scalars of GL2 from the totally real field. And these have a weight k, which has to satisfy, in characteristic 0, has to satisfy a parity condition. And these spaces have a natural Hecke action. And one can associate Galois representations to eigenforms. So these will be 2-dimensional p-adic Galois representations of the absolute Galois group of the totally real field. And the Fontaine-Mazur-Langlands conjecture predicts that every totally odd irreducible geometric Galois representation, 2-dimensional p-adic Galois representation of GF arises this way, and the weak Serre conjecture says that every mod p, 2-dimensional mod p Galois representation of GF arises this way. And then the refined Serre conjecture would predict what the weight and level should be. And we're going to focus on the weight. And there are 2 ways to generalize the weight part of Serre's conjecture. One is more algebraic in terms of Serre weights, and the other more geometric in terms of mod p Hilbert modular forms. And I've started to discuss the first of these, the notion of Serre weights. So these will be, as you've been seeing in other lectures, mod p representations, irreducible mod p representations in this case of, and I'm assuming for simplicity only that there's a unique prime over p in the totally real field, but I'm going to allow it to ramify. And then the irreducible mod p representations of GL2 of OF mod p or OF completed at p factor through GL2 of k because the kernel is pro p. And these are the mod p representations of GL2 of k. They're up to twist tensor products of symmetric powers, twisted tensor powers, indexed by the embeddings of k into Fp bar, or equivalently the maximal unramified subextension of the completion of F at P. So I'm calling the completion capital K and the maximal unramified subextension K0. So these are the irreducible representations of GL2 of this finite field. The symmetric powers have degree between 0 and p-1. And then there's a natural notion of what it means to be modular of some weight. which I formulated in terms of a quaternion algebra, an indefinite quaternion algebra, and the cohomology of the associated Shimura curve. But for the rest of the talk, that's not going to be important. This D is auxiliary. But a priori, whether rho is modular of some Serre weight depends on D. And assuming some compatibility condition on D, the set of Serre weights, according to Serre weight conjecture, should, and the mod P local Langlands philosophy should depend only on the restriction of rho to GK, and in fact, it turns out to inertia. And you can think of it, to make the connection with mod P Langlands, as the isomorphism classes that appear in the circle. So this generalizes what you just saw in Benjamin's talk, to replacing the classical modular curve with the Shimura curve. And it answers the original question about what weights, and not just weights, but what sort of local behavior at P you can expect in modular forms that give rise to the Galois representation. Okay, so I think that's where it was. So let me see now if there are questions before I move on. Okay, I give up. All right. So we're going to try and predict what the set of weights with respect to which rho was modular is going to be. And we'll do it as in the classical setting. We'll formulate it using p-adic Hodge theory in terms of whether the local Galois representation. So remember, K was the completion of F at our unique prime over P, in terms of whether the Galois representation has a crystalline lift with labeled Hodge-Tate weights. Maybe I won't remind you what labeled Hodge-Tate weights are. That are in some sense compatible with the weight appearing here. So remember, these labeled Hodge-Tate weights were the ones appearing in the description, well, in the statement of local global compatibility at primes over P in the description of the Galois representation associated to a Hilbert modular eigenform. But and so first, consider the case where P is unramified. So remember, the i's here run from 1 to F, or run through Z mod F, and they correspond to embeddings of little k into Fp bar, and they're F of those. And J runs from 1 to the ramification degree E. So if P is unramified, you can ignore this. And this is in some sense what you would expect. And there's no additional information here in the ramified case. And the labeled Hodge-Tate weights at the other embeddings we're going to stipulate should look like they come from p-divisible groups, or weight 2, or there should be 0 and 1. So this is G's insight, in one of his insights in generalizing to the ramified setting. So this is the so this depends only on the local Galois representation and characterized using p-adic Hodge theory. And then the conjecture is that this is the set of weights with respect to which rho is is modular. And then there's this Meyer compatibility condition on the quaternion algebra. So this, as I said, this formulation is due to G, and it generalizes a more explicit version in VDJ. In the case when P is unramified in F, the crystalline liftability being implicit in our more explicit definition. And generalized also in a more explicit way to the ramified setting by Schein under the assumption that rho, that the local Galois representation is semi-simple or maybe just semi-ramified. And you can make this set quite explicit in general in the unramified case. I did this with Dembele and Roberts, or at least conjecturally, and then the conjectural description was proved by Caligari, Emerton, G, and Malvidis. And then in the ramified, so in general, by Steinmetz. And as I said last time, this is essentially a theorem, at least if you assume that rho is modular. So if rho is modular, then the conjectural weights are precisely those for which rho is modular in this sense. And so in particular, it's independent of D. There's also a Taylor-Wiles hypothesis, because as you'll see in my, well, I won't even call it a sketch, my few words about the proof, that it relies on automorphy lifting theorems and so on Taylor-Wiles hypotheses for rho. Okay, now before I say a little bit about the idea of the proof, let me explain how to make this, this set of Serre weights more explicit in the simplest case beyond F equal Q, that of a unramified quadratic extension. And let's see what these sets of Serre weights look like for a Galois representation for a locally reducible mod P Galois representation. So you can twist. So all this machinery is compatible with twisting. So we may as well twist so as to assume that there's an unramified or trivial even quotient. And so we have characters on the diagonal, psi and trivial, and the restriction of psi to inertia is going to be a power of this fundamental character, now of order p squared minus 1. We can write it as a power of omega 2, so omega 2 being defined either using class field theory or by looking at the action on the p squared minus first root of a uniformizer, which in this case you can take to be p. But there are actually two fundamental characters indexed by the embeddings of k. So the fundamental character takes values in the residue field k, and you have the two possible embeddings of k into fp bar. So I'm going to choose one, tau 0. Maybe I've already chosen one, tau 0, and then you can write the p-adic digits of the exponent here as a0 and a1. a0 plus a1p being between 1 and p squared minus 1. Actually, I want to take it to be between 2 and p squared minus 1. And then it's fairly easy to see that this sort of representation will have a crystalline lift with these labeled, well, with labeled Hodge-Tate weights a0 and a1. Well, the tau 0 labeled weights will be a0 and 0, and the tau 1 labeled weights will be a1 and 0. And if you translate that, if you go back to the recipe for w of rho, that translates into this being among the Serre weights for this representation rho. So remember, there's a shift by 1 as well. So, and that's why I'm assuming that A0 and A1 are at least 1. And the problem with A0 and A1 equaling 1, so where you would expect the trivial representation to appear here, is that there's a condition on the star, which you've seen before. Actually, it would need to be paramétrié. But if you look to see, if you try to understand what other possible weights of, what are the possible crystalline lifts with small Hodge-Tate weights or small differences of Hodge-Tate weights can arise, you see that it depends on the extension class. And for simplicity, I'm going to rule out the cases, the most extreme cases where the character is unramified or cyclotomic on inertia, which corresponds to the cases where A0 and A1 are P, and A0 and A1 are P minus 1. And the extension class just corresponds to, you can think of it as a Galois cohomology. So the star corresponds to a Galois cohomology class with coefficients in this one-dimensional representation defined by psi. And this space has dimension 2, the 2 being the degree of k over qp. And it's 2 and not bigger because we ruled out these exceptions. And then to see what other what other small weights of crystalline lifts can arise, what you can do is twist the representation in such a way to get small powers of the fundamental character on the diagonal. It's elementary to see that you can rig this in a unique way so that the A0 prime and A1 prime, these exponents are again between 1 and P, and determine when there's a crystalline lift. And it turns out that this is equivalent to the existence of a crystalline lift with the corresponding labeled Hodge-Tate weights is equivalent to the extension class being in a one-dimensional subspace, being in some line inside this two-dimensional space. So there's this constraint on the extension class for there to be another Serre weight in the list. And you can do the same thing, just interchanging the roles of the two embeddings to see that you get yet another weight if the extension class is in another line. And the two lines, and then this will you'll see this again later, the two lines turn out to be the same in situation when one of these indices is P, otherwise they're different. And you can have even more weights. You get another weight if the representation splits, because you can twist by psi inverse. And write the representation as psi inverse tensor, write it as psi tensor 1 plus psi inverse. And write the p-adic digits of psi inverse, the exponent, if you write psi inverse as a power of omega. I guess you could have even more if psi happened to be the inverse of the cyclotomic character. Okay, so you see the structure of the set of weights. It is somehow richer than in the case of F equal Q, and that's appearing in the representation theory of GL2 of GL2 of capital K. Well, it's appearing in the analysis of what representations you're interested in the context of Montague-Langlands. Okay, so now let me just say a little bit about about G and collaborators' strategy for proving this equality. So the idea, one of the key ideas, is to use automorphic lifting theorems to prove the existence and automorphy of potentially barsodic Tate lifts. So one's corresponding to weight 2 modular forms, but possibly with level structure at P. And to play off the relation between weights and types that's implicit in the Fontaine-Mazur conjecture, to get an equality not between not between the set of modular weights and the conjectural set of weights, but some other set that's defined in terms of potentially barsodic Tate lifts. And then finally, using p-adic Hodge theory to show that you've actually got all the weights this way. So weight elimination to show that, in fact, equality holds here. And let me just explain this in somehow the simplest example, a toy example, because it gives a new proof of the companion forms theorem for F equal Q. So remember that you expect companion forms to exist when your representation is tamely ramified. And so suppose your restriction to so we'll look at the reducible the reducible situation, so that rho is on inertia is the sum of two characters. And this looks like it should come from weight K. So that's weight sim K minus 2. And it should have a twist which comes from another weight, but let's try and prove, so you can treat each of these by twisting. So let's try and prove that this representation actually arises from weight K, from weight sim K minus 2. And the idea is, instead of proving directly that it has a lift of, instead of proving directly that it's weight, that it arises in weight K, you prove that it arises in weight 2. Use an automorphic lifting theorem to prove that it's modular of weight 2, level P, and character chi tilde being the Teichmuller lift to the K minus 2. Or in terms of types, it's this, this principal series type. So then from this modularity result, that it's modular of this type, it follows from what I was explaining in previous lectures that it has to be modular of some weight that's a Jordan-Holder factor of the reduction of this type. And these are the Jordan-Holder factors. And in particular, sim K minus 2 is a Jordan-Holder factor, but so is this other representation. So you know it's modular of one of these weights. but it can't be modular of this weight. Because it doesn't have a crystalline lift of that weight, would be one way to say it. It's not among the predicted weight. So therefore, it's modular of the weight that you want. So in general, the proof is much more involved because you need, first of all, more general automorphy lifting theorems. It's not enough just to know the list of types with respect to which rho is modular of weight 2. You need the finer information of the Bordeaux-Mazur conjecture, which the relevant cases of G and Kissin prove in the course of proving the weight part of Serre's conjecture. And then the p-adic Hodge theory is also much more difficult in papers of Gilu and Sabat. Okay, so now I'm going to switch over to the geometric Serre weight conjecture. So first to set things up. So remember, the idea now is to formulate a version of Serre's conjecture in terms of geometrically defined mod P Hilbert modular forms in such a way that you can also, for example, see modular forms of partial weight 1. And so first of all, we need, we're going to need integral models of the Hilbert modular varieties that we're going to reduce modular P. And so I'm going to allow P to ramify. And so smooth models are defined by Pappas and Rappaport. And I'm going to continue to assume that there's, to simplify the notation, I'm going to continue to assume that there's a unique prime dividing P. So I think the models were, so in the unramified case defined by Rappaport, I believe. But the sort of naive models, well, I don't know what to call them naive, but the models defined by the models used by Rappaport were not smooth if P is ramified in a totally real field. And the idea in the ramified setting is to introduce filtrations to resolve the singularities. So let me briefly recall how that works. So the moduli problem associates to local Noetherian schemes over O isomorphism classes of data, where A is an abelian scheme of dimension D with an action of OF, and lambda is going to be a quasi-polarization compatible with the OF action and of degree prime to P. And eta will be a level U structure. So this is standard the standard data in the definition of moduli problem for PL-Schmor varieties, except I'm not specifying the polarization module. I'm only requiring that it be degree prime to P. And then the additional ingredient here to deal with ramified, to deal with the possibility that P is ramified, is to introduce a filtration as part of the data. So a filtration on each component of the invariant differentials. And the successive quotients should be line bundles on which OF acts by theta ij. Remember, I've just chosen an ordering of the extensions of each tau I. So this forces the component. So the differentials have an action of OF tensor OS, and in particular OF tensor O, and so decompose according to the embeddings of the unramified subextension. So the existence of a filtration is going to imply that each of those pieces is locally free over OS of rank E, but not necessarily free over OF tensor OS. But the successive quotients will be line bundles that we'll use to define the automorphic vector bundles later. But let's see. So this is representable by a scheme YU tilde, which is smooth of relative dimension D over O. And I've done something a little non-standard in not specifying the polarization module, and so in fact we're getting an infinite disjoint union of the usual PL-Schmor variety, Hilbert modular varieties. But there's also an action of the units in the localization, so the prime to P elements of F cross, acting on the polarization. So I'm forgetting the polarization. I'm going to take the quotient by this action. To get a model for the Hilbert modular variety YU. And the advantage of this setup is that you get a Hecke action from the construction. And then reduce mod P, or not mod P, but mod the uniformizer of O. So we're looking at the special fiber, and we're going to look at automorphic vector bundles on the automorphic line bundles on the special fiber. And then our mod P Hilbert modular forms will just be sections. So from the moduli problem, we have we automatically have line bundles indexed by the embeddings on this infinite cover. And you also can define line bundles that we'll want to twist by. So these are just determinants of some rank 2 subquotients of the de Rham cohomology of the universal abelian variety over yu tilde. And then this automorphic vector bundle AKM pulled back to this yu tilde and viewed over the complex numbers is just this. But with this setup, you also see that for an arbitrary O algebra, these line bundles descend under the assumption that this character is trivial on the units in this open compact subgroup, the global units in this open compact subgroup. So the non-vanishing, the non-triviality of this character is the obstruction to descent when you mod out by the action of the units. So in characteristic 0, you can view this as where the parity condition is coming from, because this is only going to be trivial when k theta plus 2m theta is an integer independent of theta, in which case this is just the power of the norm. However, in characteristic P, as long as u is sufficiently small, this condition is automatically satisfied, and so these line bundles will descend to the Hilbert modular variety that we're interested in. And now there's no condition, there's no parity condition on K anymore. And then for any K and M, we can then define, and sufficiently small level U, we can define the space of mod P Hilbert modular forms, the geometric mod P Hilbert modular forms, just to be the sections of this line bundle. And also, we don't need to worry about compactification by the Coker principle. So we can just define modular forms to be sections on the open Hilbert modular variety. And the presence of the M here is just going to, well, it corresponds to the, notice that in my notation for algebraic weights, I had M comma N, so the order is changed, but I'm being consistent in this M, which is just twisting in the same way as in the algebraic setting. But it's convenient to carry around to keep track of Hecke action. So then we can take the direct limit over all open compacts of level prime to P and get a smooth admissible representation of GL2 of the finite adels prime to P on this direct limit. And so we get Hecke operators on this space, on this finite dimensional space. So we can talk about Hilbert modular eigenforms in characteristic P. Maybe I should point out that the representation theory is gone here, because the level here is prime to P. So we can't take a limit over open compact subgroups of GL2 of OFP here. So we've lost the representation theory, but we have geometry instead. So in particular, we have Hasse invariants. We have generalizations of the classical Hasse invariant defined in the setting by Reduzzi-Xiao, building on a definition in the unramified case by Goran, and refining a definition in the ramified case by Andreatta and Goran. So how does this work? How do you define the Hasse invariants, the partial Hasse invariants? So take a uniformizer at P, and the action of the uniformizer on the universal Hilbert-Blumenthal-Abelian variety maps each step of the filtration into the lower into the lower step, and so induces a map on these line bundles. So this is happening because we're working in characteristic P. You can think of these as modules for O pi mod pi to the E, where E is the ramification degree, and multiplication by pi is moving you down in the filtration, even though this might not be free over O pi mod or OS pi mod pi to the E. So this induces a map on the line bundles, and that is the Reduzzi-Xiao partial Hasse invariant for j greater than or equal to 2, because this quotient would be well, there'd be no quotient here if j is 1. And you can think of this as a section of this line bundle, Lij inverse Lij minus 1. And then for j equal 1, remember how the classical Hasse invariant is defined. It's induced by the Verschiebung, and in this case the Verschiebung. So it's going to drop the index I by 1, and in the component. So this is implicit in the twisting by Frobenius. But it's not hard to show that a Hasse invariant that you might define this way. So I think this is the one defined by Andreatta and Goran on the Deligne-Pappas model, reduction of the Deligne-Pappas model, but it factors. You can divide by pi to the E minus 1, essentially. So these being the Hasse invariants, the partial Hasse invariants that were just considered, and this defines, or can be taken as the definition of the partial Hasse invariant corresponding to the embedding theta with j equal 1. And the ordering of the embeddings here was arbitrary. This construction doesn't really depend on so the HIJs depend on J, but they don't depend on how you match, how you order the embeddings theta. So HI1 then is a section from, I should have pointed out, this is from LI1. So these are each dropping, these are going from Lij to Lij minus 1. So this is going from Li1 now to Li minus the pth power of Li minus 1e. And these constructions don't depend on the polarization. They're compatible with the descent data. And so they define elements. In fact, they define modular forms. They define sections of the line bundles. What did I call them? A bar H theta 0, where this is the weight of the partial Hauss invariant. So it's 0 everywhere except at theta, it's -1, and at the preceding index, it's either p or 1, depending on whether j is 1 or bigger than 1. So that's written out here. So sigma inverse theta is just the preceding index in this cyclic permutation of the set of embeddings. And as I said, the coefficient here is p or 1. Oh, and the e thetas are just the basis vectors corresponding to theta. So not only are they compatible with descent, but they're also invariant under, there should be an upper p here, but they're invariant under the Hecke action. Okay, so now what I want to do is so we want to formulate a geometric Serre weight conjecture. So we have our objects, we have our mod p Hilbert modular forms. For this to be reasonable, we want to be able to associate Galois representations to mod p Hilbert modular eigenforms. So suppose we have such an eigenform. There is an associated Galois representation, characterized in the usual way by being unramified at primes different from p in the level and not dividing the level, and having the characteristic polynomial that you expect, where AV and BV are the eigenvalues of TV and SV. So this was proved by Goldring and Koskevierta and Hamilton, Reduzzi, and Xiao with a parity hypothesis on K. And what Sasaki and I did was to remove the parity condition to be able to talk about complete sets of weights. And what I want to do in the remaining time today is sketch the proof. So the strategy already in Emerton, Reduzzi-Xiao is to multiply by partial Hauss invariants in order to shift to a weight that's, well, ideally you want to shift to parallel weights so that you know that the corresponding line bundle on the integral model, well, let's say in the unramified case, this needs to be modified in the ramified setting. But to shift to a weight for which the corresponding line bundle is ample so that you'll be able to lift to characteristic 0 with a high enough power. But the problem, if you want to remove the parity condition, is that you see from the weights of partial Hauss invariants that you can't necessarily do this in such a way to reach a weight which is pernicious. For example, if D is even, then shifting by multiplying by partial Hauss invariants won't change the parity of the sum of the weights. And so the sum of the weights will always be even. So that would rule out starting with a weight so for which the sum of the indices, the sum of the k thetas is odd. So the way we get around this is to, instead of multiplying, instead of using forms which have level prime to p, we're going to show that our eigenform lifts to some precise weight now with level u1 of p. And let me at first assume that p is unramified and explain how the proof works in that case. So you can twist to get rid of the m. And so for sufficiently small u, the descent of the n thetas is trivial and is just keeping track of the Hecke action. Okay, so forget about m. And then you can multiply by these partial Hasse invariants. As I said, you can't necessarily reach a parallel weight, but you can reach a nearly parallel weight. Some large, nearly parallel weight, nearly parallel in the sense that so this n here is n in each component, so it's a parallel weight, and these delta thetas are small. They're between 0 and p minus 1, and not all p minus 1. So this is just a congruence condition. It's easy to achieve this. It's easy to see you can do this by multiplying by partial Hasse invariants. And then to make sense of, to have a chance of lifting to weight involving p, we're going to need models for the Hilbert modular varieties with p on the level, defined by Pappas. So we have the projection map. So the y0 is parameterizing p isogenies, suitable p isogenies. And y1 is just finite flat over y0. So the y0 is a flat local complete intersection. And y1 is just a closed subscheme of the kernel of the universal isogeny in the definition of y0. But in this situation, pi 0 is not finite or flat. On the ordinary locus, it is, but off the ordinary locus, on the supersingular locus, it's decreasing dimensions. But the yi's are Cohen-Macaulay, so we can talk about their dualizing sheaves. And in fact, over the generic fiber, when you invert p, these dualizing sheaves are described by Kodaira-Spencer as in the usual way as modular forms of weight 2. But let's keep track of the Hecke action. And then, so we want to relate, let me back up for a second. Now we want to somehow absorb the delta into level p. And you can somehow see that in the dualizing sheaf. So you have a canonical section defined by the kernel of Frobenius. So this is a familiar identification in the classical case of one of the components of the reduction of y naught of p. with the modular curve of level prime to p, of y naught of np and y naught of n. And just from well, this is a case of Grothendieck-Serre duality here. That the push forward of that the direct image of the dualizing sheaf under this finite flat morphism is just the dual of the push forward of the structure sheaf tensor with the dualizing sheaf downstairs. But remember that that y1 bar is just a subscheme of the kernel of the universal isogeny, and that lets you relate it to these line bundles, these small weight line bundles. And so you get from this an embedding of these bundles in the push forward of the dualizing sheaf, or maybe you want to think of the adjoint. So that now twisting, there's a twist by the, remember K was what? It was n minus delta. So this times this embeds in well, the pullback here. We can map the pullback of a n minus delta to K1 bar, tensor the pullback of this automorphic line bundle with parallel weight. And then, so now we've reached parallel weight with some at level U1 of P. You want to lift to characteristic 0, and there's still some work to do. But using the ampleness on the minimal compactification to prove that some H1 vanishes, together with the vanishing of the higher direct images of the canonical sheaf, which we proved. So this is with Kasai and Sasaki. So you still need to commute the reduction mod p and the direct image. So you show that the image. So this is, I think this is not necessarily. So this reduction mod p here is not necessarily surjective, but the with a little work you show that the that the image under this inclusion is contained in the image of reduction, so that lets you lift the characteristic 0. And now a standard argument shows that you can actually lift to an eigenform. So once you've lifted to an eigenform, you have an associated Galois representation, which you can then reduce to get the Galois representation that you're interested in. Okay, just a few words about what to do in the ramified case. So, so you sort of combine this idea of shifting to a nearly parallel weight with the idea in Emerton, Reduzzi-Xiao in the way they deal with the ramified, case, which is to twist by these bundles. So the parallel weight bundles are no longer ample. You need bundles for which the weights are increasing with J. And in in the analysis of the duality of the dualizing sheaf, it's the top, it's the theta IEs that appear. So this is where you want your nearly parallel parallel weight to be reflected. And then it's not even quite true that the space of forms that you get is contained in the image of reduction, but if you just look at cusp forms, it still works. It's contained in the image of reduction, so you can lift a characteristic 0, but then you need a separate argument if you want the result in the generality that I stated. You need a separate argument to deal with the contribution from the cusps. Okay, so that's a good place to stop, and I will continue next time with the formulation of the geometric Serre conjecture.
So thank you very much, Fred. Are there any questions? I see Mladen has turned on his camera.
Now I have to ask a question.
Go ahead.
No, it was all crystal clear again for a third time. I just have a small question comment. Do you hear me? Okay. Well, you said like you want to go to a nearly parallel weight, but then you put m vector equals 0, so you're in parallel weight.
No, but the k is not parallel.
Okay. If the k
so
is
k
not
plus 2m, so there's no so k plus 2m is just
okay. Then I have a real question, which is like, suppose you started with a mod p eigenform which is not a cusp form, then you have no chance to lift it to characteristic 0 unless you go to a parallel weight, right? You know this, of course, yeah.
If you start with a mod p cusp form, sorry, say it again.
No. You start with a mod p form which is not a cusp form. It has a non-zero value at some cusp, okay? Start with the eigenvalue, with the eigenform mod p, which is not a cusp form. Then, because in characteristic 0, eigenforms which are not cusp forms are necessarily in parallel weight. Eisenstein series are necessarily in parallel weight. Your only chance to lift this form in characteristic 0 would be in parallel weight.
Yes, but it's parallel weight with a p in the level.
Okay, but it's parallel.
It'll be parallel, yes.
Okay, as long as it's parallel.
So this is part of why it breaks down in the ramified setting.
Okay.
So you won't be able to lift. Yeah. So then, yeah, you need a separate argument.
I just didn't understand this thing of the nearly parallel, but eventually go to a parallel, because otherwise it won't be possible. Okay.
So in the ramified case, you don't go to a parallel weight, you just go to a Paritius weight.
But then
you're cusp
forms. So the statement is only about cusp forms then.
No, but you can still prove it in general for modular forms by a separate argument, just by analyzing. If you look at the co-current, you can understand, you can analyze the Hecke action and see that even if you don't, so you're not lifting. So this is maybe this one. We'll deal with it. So you're not actually lifting the eigenform. You're just the separate argument just analyzes the possible Hecke eigenvalues and shows that they are in some sense Eisenstein, and therefore there is an associated Galois representation which you can just construct by hand.
Okay.
Yeah. So that.
Okay. Thanks.
Any more questions or comments? Okay, great. So thank you very much, Fred, again for that third talk. And we will see all of you tomorrow morning at 9 in India, 9 a.m. India time. So I will not try and count how many hours that is from now. But yeah, let's see. 15 hours from now. Get a good night's sleep, at least for the Indians. All right, bye. Thank you.
Okay.